Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. In the second part of the lecture, we'll have another application. It is kind of related to what we discussed, but it's a different problem. This problem is called pairwise document similarity. What do you mean by pairwise document similarity? Let's first have some definitions and then we'll come back to the actual definition of the problem. In IR, or in document processing in general, we tend to represent documents as vectors. And that makes processing and computations a lot easier. So every document will be represented as a vector of numbers. Okay. Now what are these numbers? This number, there will be a number for each term in the entire collection. Let's assume that for now. And let's say that we have 1 million unique term in the collection. There will be a number for each term, and that number will be like a weight for that term. You can think of it as an importance weight. If the term is important in that document, it will have a higher weight than non-important terms. And of course, the terms that didn't appear at all in the document, it will have zero weight. Okay, and that will be enough for us to think about this vector. Okay, so again, each document will be a vector, and the vector has one number per term, and you can think of it as a weight, which indicates the importance of that term. Now, if we, of course, this vector is sparse, lots of zeros again, and you can think of it generally as a feature vector. If you are familiar with the machine learning or data mining, usually we represent examples or samples as vectors. We call them feature vectors. Okay? So we use this terminology also. But for now, think of it as just a vector of weights. So what is the abstract problem now? Remember, the problem is called pairwise document similarity. We want to compute similarity between every pair of documents in a collection. That's the main problem here. Okay? So if we think of it the way that we just mentioned, every document will be represented as a vector. So now instead of collection of documents, we have collection of vectors. And now we want to compute the similarity between every pair of documents. So every green line here indicates the similarity between a pair of documents. So we want to compute all of these similarities.
This is like feature selection in machine learning.
Feature selection is like that.
Well, you would determine the correlation between the different features in order to select the feature.
You can think of it that way, or actually it's maybe easier to think about it. Is like in clustering, we want to compute similarity between every pair of items, right? So that we can cluster them together. So there are many applications for that, by the way. And this is the abstract problem, but there are many applications. I listed some of them here. One application is what we call near duplicate detection. In a collection, there are documents that are very similar to each other. We want to detect them. Sometimes they are different, very different. They are just different in few words. You can think of that like, and we see that many times. The same news is copied over different websites. Okay, maybe with different ads or different headers. Okay, so we call this near duplicate detection. We call these near duplicates, and we want to detect them. So one way is to compute similarity between these documents. Clustering, as I said. Another nice example here, or nice application, is friends recommendation in Twitter or Facebook. In that case, every document is not actual document. It's just a user. And we represent the user as a feature vector. Okay? And in order to recommend different users to different people, we need to compute similarities. Once we compute these similarities, we can recommend similar people to the users. Okay. Another or fourth application is what we call more like that queries. Sometimes when we search, we get some search results. We click on one document, and we liked it. Okay, we found that this is very relevant to what we want. Okay, so we want to see more like this one. That's the application here. Okay, more like this one is like very similar to that one. So we want to detect those that are very similar to this specific document. So that again, the abstract problem here is to compute pairs of similarities. Okay, and there are many applications to that problem. Now, how can we compute similarities in vector space? So we call this, by the way, model. I forgot to mention that. We call that model in which we represent every document as a vector, we call it vector space model. Okay, so in VSM or vector space model, the similarity is computed by the dot product between the vectors. Okay, so we represented each vector as a weight, each document as a weight vector. We just compute the dot product. Dot product means it's sum over the individual or corresponding weights for each term. So that summation here is done over the entire list of terms in the collection, in the vocabulary. For each term, we compute, we multiply the weight of that term in the first document with the weight of that term in the other document.
Isn't this like Euclidean distance?
No, Euclidean distance you subtract and you square. That's not the Euclidean distance. This is very similar to what we call cosine similarity. Okay, but forget about the naming. It's just dot product between the two vectors. And that's an indication of similarity. Okay? And that represents actually a large class of similarity metrics. As I said, cosine similarity, there are also in IR other similarity functions like BM1025. But forget about the naming here. Let's focus on the abstract problem. We want to compute this kind of similarities between every pair of documents in the collection. And this is how we compute it. Let's assume that we already computed the weights, so we're not bother ourselves with how the weights are computed. The weights are given, and we have these vectors for each document. How can we compute the pairwise similarity? Okay. Here is a trivial solution. So what could be a trivial solution, by the way? Let me, before I show it. What could be a very, very trivial solution? Not thinking about MapReduce completely. If I gave you that set of documents and I told you, compute the pairwise similarity, what would you do? The first implementation. I gave you n documents, and I asked you to compute the pairwise similarity, the way that we showed here. The similarity is just the dot product between the vectors. What is the first implementation? That doesn't have to be efficient. Yes.
Read the documents.
Read the documents. So we upload the vectors in memory. Then.
Compare.
Huh?
Okay.
Compute the dot product between each one and all the others. Very good. What is the complexity of that? So how many loops we have here? How many nested loops here? So every document, we get every document and we compute the similarity between this document and every other one, right? And then we switch to the next one, then the third one. So that's two nested loops, right? Because we need to compute between every pair. If we have n documents, then the complexity of this is order of n squared. Okay? N squared. Okay? So that's it. So we upload all, we trade over the pairs, we get order n squared. But of course, that requires that we have all the vectors in memory, and also the similarity matrix must fit in memory. If we don't have enough memory, of course, we have to resort to disk. Right. And remember this, we need to load every vector order of n times. Right? Because one vector will, if we do it on disk, okay? If we do it on memory, خلاص, everything in memory, but that's not scalable. But if we do it on disk, then we upload one vector, and then we upload all one by one to compute the similarity. And then we switch to another vector, we upload one by one again, and so on. So every vector will be loaded order of n times, which is a huge number. Can we optimize these computations? Of course, yes. Let's think together how we can do it. Let's first look at this this similarity function. We said that this is over the entire list of terms, right? Is it actually the case that it is it's over the entire list of terms? Look at this equation or this function. It's the sum over all terms of these weights. What are these weights? And for two documents di and dj, these are two vectors, right? Let's say that this is I and that's j, and this is over all terms. The terms are here, right? So these are the terms, and every term has a weight, and we compute these weights. We get these weights, and then every two weights here we multiply them, and then we add to the previous ones. So take every pair of these will be multiplied and added together. Okay? If you think about this operation, is it actually over all terms in the vocabulary? When will we, what are the values of these weights? What are the possible values? We said that these weights are either 0 if the term didn't appear in the document, or positive if it appeared, right? Right. If one of these terms are 0, if one of these weights is 0, what will happen?
Product is 0.
The product of these two is 0. Whether the other one is 0 or not, then it doesn't matter, right? Type. If that's the case, then what is this set exactly? What is a tighter set that still can give us the exact value?
The weights in both are not 0.
Very good. The weights in both are not 0. Okay. What is the meaning of that? When the weights are not 0, what does that mean?
They appear.
They appeared in the document, right? They appear in the document. So that means that each term contributes only if it appears in both documents. If it appeared in just one of them, it doesn't contribute to the similarity of them. Similarity between these two documents. Okay? Is it clear? Good. Type. So we can replace this T belongs to V to just T belongs to the intersection of them. Okay, which means both documents. Okay. So I can just replace this by the logical meaning of it, which is the term contribution of T, that's the contribution of T in the similarity of these two documents, which is the multiplication of the weights of that term in both documents. Okay. Can we benefit from that? Can we think now differently to make the trivial solution that we saw in the previous slide more efficient? In the previous slide, we said that we will get one document and compute the similarity between this document and every other document. Right? Right. Now we said that we don't need really probably the entire vector. We just need the terms that are common. And for these terms that are common, we need to multiply their weights. Okay? And those terms that are common are the only terms that will contribute to the similarity. Every term, any term that is not common between the pair of documents will not contribute. Okay? Because at least in one side it will be 0, and 0 times anything is 0. So how can we benefit from that? Any ideas?
Why don't take from the vector itself, from the document, we exclude the zeros.
Okay, so that's by default, yeah. We assume that we can, of course, exclude zeros. So it will be like the posting list in the first part, right? So we don't have the zeros, we just have the weights for the terms that appear. Okay, how can that benefit us? Where are you? What happened?
No, I just have to take a call.
Okay, it's a long call. Is that international call or what? Okay. So can we benefit from the fact that only terms that are that appear in both documents will contribute to the similarity of that document, of this pair? Is there a way to know? Let me give you a hint. Is there a way to know for a given term which pairs of documents this term will contribute to their similarity? Concurrence of what? No. Okay. When can we say that this term will contribute to the similarity of these two documents? We said that when this term appeared in both, right? Right. Where can we get the information that tells us this term appeared in that document and that in that document and in that document? Huh? From the vector, but not directly, right? The vector is document term. Okay? From the postings. From the postings. Okay? So that information is in the postings. So if we have the postings, now we can think of the solution in an inverted way. Previously we said that we will have two loops, and we go over each loop will go over the vectors, the documents, right? Here it's not the case. Here we will loop over the terms, not the documents. Yes, because every term will contribute to some of the documents. The similarity of some of the pairs of documents. Okay? And as you said, we will know that from the postings. So let's assume that we have the postings for each term. So that means that we know for every term what are the documents that had this term. Now, what is remaining is how we can say that, how can we get the contribution of that term in all pairs of documents for which this term will contribute to its similarity. Let's think together. I forgot to do that. Okay. Now we have. Let me do it here. Let's say that term like Qatar appeared in these documents. So this word appeared in 4 documents only. And let's assume that here we have the weights also. And beside each document number, we have the weight. So that's the posting. So we have some weight here, we have some weight here, we have some weight here, we have some weight here. These are the weights of that term in each of these documents. Okay? So these are the postings that we have. Can you tell me which pairs of documents this term Qatar will contribute to their similarity out of these postings? Okay. We have this posting list. Okay. Qatar appeared in 4 documents, and these are just the document IDs, W, X, Y, Z. And we also have the weight of Qatar in each of these documents. These are the weights. Okay. So let me do it in a better way probably. Let's have these weights. 2, 1, 3, 2. Okay, so these are the weights. So this is the weight of Qatar in the document W, this is the weight of Qatar in the document X, and so on. Okay, now my question is, can we know from that the pairs of documents that Qatar will contribute to their similarity? We can't. Why we can't?
Because we represent the documents as a vector with the weights. And, if weights are term frequency, then how would you know that weight is related to some term Qatar?
This is no. This is given. This is the posting list now. This is the posting list for Qatar. Okay, so we know that the weight of Qatar in W is 2, the weight of Qatar in X is 1, and so on. So these are the weights from the vectors. We represented the vectors in that way. Okay, so the same information is encoded here. Now, again, the question: can we know which pairs of documents Qatar will contribute to their similarity? Yes.
Shouldn't it be each of those pairs, WX, WY, WZ, XY, XZ, and YZ?
Very good. Why?
Because we need to form pairs of 2 from each of them.
Yes, because this posting list means that Qatar appeared in W and X, right? So it will contribute to the pair WX. It also appeared in W and Y, and W and Z, and X and Y, and X and Z, and Y and Z. Right? Type, what is the contribution in each? For example, W and X, do we know the exact contribution of Qatar to its similarity? Yeah, it is 2 times 1, right? Because we have the weight here, and we have the weight here. So it will be 2 times 1. How about W and Y? 2 times 3. And so on. So that's the partial contribution of Qatar for these pairs. Type, is there any other pair outside these that Qatar will contribute to?
No.
Are we sure?
Yes, after the review,
No, we didn't talk about MapReduce yet. Okay, it's just the idea now. Okay, there's no map here and reduce and nothing.
the posting list have all the
Yes, we have. Yes, in the posting list we have all the documents in which this term appeared. Is there any possibility that there are other pairs that we didn't have here?
As per the example,
Huh?
as per this example, no.
Yes. So if we are given the entire posting list, then we can generate from that posting list all the pairs, right? And this will be the partial contributions. And that's exactly what we have here. So we get the posting for all pair of documents in the posting list. We will add to the similarity of documents I and J. Here I forgot to say that we have a huge matrix here. Okay, that is initialized with zeros for every pair of documents. Now we will add to that the contribution of T in the pair I and J, which is the weight of T in DI times the weight of T in DJ. We'll add it to that similarity. So for that solution, what happens is that we don't multiply weight vectors. We actually compute the partial multiplications. We compute the partial similarities or partial contributions. Okay? So is that algorithm clear? I mean, do you think now that this will give us the same values that we got from the trivial solution, which is just computing the similarity between vectors directly? Would that give us the same values? Assuming, of course, that we will go through all the terms. Okay, so this, for example, for a specific pair of documents, all the terms that are in the intersection between I and J will have their contribution. Remember that when we said that we only need to look at the terms that appear in the intersection? Is that guaranteed here?
No.
Why not?
Maybe in one vector we'll find 0.
And will we miss one of the terms that are in the intersection? Where are the terms that are in the intersection? Okay, let's say that we are talking about documents 10 and 33. Okay, and document 10 and 33 has the words A and C and K in common. Only those are in common between 10 and 33. Okay, now let's look at this algorithm and see if we will actually have these contributing to 10 and 33. And only these, not any other term. Let's look at the other terms first. Let's look at the term B that didn't appear in both. Maybe appeared in one of them, but not in both. Okay? So term B we will get to it sometime, right? In that loop. Let's say that T is B now. Okay? So T now is the term B. We'll get the posting list of B, and then every pair that appeared in this posting list, B will contribute to. Now, will we get 10 and 33 out of this? Can DI be 10 and DJ be 33 for the term B? No, because we assume that B is not in the intersection, right? So 10 and 33 will not appear here at all. So B will not contribute to that pair. Type. Let's now take one of these. Let's take C. So now this is not B, this is the term C. We get the posting list of C. Now since C appeared in both 10 and 33, then of course one of the pairs here will be 10 and 33. So C will contribute to that. Okay? So are we missing anything now? No. So this will give us exactly the same values. But what is the advantage of this? We don't need to load a vector n times. Okay, we'll just load the posting list for one term and then go over it and add the partial contributions to the similarities. So that's more efficient, but still there is a bottleneck. The bottleneck is that this similarity matrix has to fit in memory. We have to have this matrix so that we can add the partial contributions to it. If we cannot fit that in memory, then we'll not be able to have this. Okay. So is that algorithm clear? Okay, keep that in mind. Now, the goal is to have a scalable and efficient solution for large collections. So that will be good for small collections, that the matrix will fit in memory. Remember, the matrix is, what is the size of the matrix? If we have n documents, what will be the size of the similarity matrix? N by n, right? Which is n squared. And if we have 1 million document, which is a small number of documents, 1 million by 1 million, right? That's a huge size. Okay. So we need a scalable and efficient solution for large collections. MapReduce comes to the rescue here. How can we do it using MapReduce? Here's the algorithm. Okay. Any ideas first? Let me ask you. How can we do it? We get the postings. How can we get the postings? So we need to do the indexing. The part. Very good. Yes. So we'll have to do the indexing first, as we did in the first part of the lecture. Okay. And then this will be the input to another MapReduce job. So that's the first application in which we see a pipeline of more than one MapReduce job. So we have the indexing first, and then we have another job. Now, what will be the other job? What will we do in the other job?
I think the other job will have as an input, the posting will be term, post.
Yes, so the key will be term. That's the output from the indexing, right? The output from the indexing is the term is a key, and the posting list as a value, right? That's what we discussed in the first half, right? Now this will be input to the next MapReduce job. When we say this will be the input, then what will be the input to the map function? To one map function? The term and the posting list, right? Okay, the term and the posting list. Now what should we do with that? Yes, looking at this postings, the partial contribution, right? So we can, for each pair here, for each pair in the posting list, we will compute that partial contribution. Then will we have the matrix? Huh?
No, we just emit it.
We just emit the partial contribution. What? Yes, this is exactly my question now. What will be the key? Two documents. Document I and J, that will be the key, and the value. This partial contribution, which is the multiplication of the weights. If this is the case, then what will happen after the map? Yes, all partial contributions will be grouped by the pair of documents, and then the reduce will just sum. Okay, so that's the main idea. So these are the partial contributions. We can compute them independently, and then we aggregate at the end. Okay. And we can do that for each term in parallel. So that's the map phase. Okay. So the map phase, of course, this part can be done completely in parallel. Okay. We don't need to do any interaction here. Each term will produce all of its partial contributions at once in the map phase. Then the aggregation will happen in the reduce. And of course, the condition here, so that's also for each document pair in parallel. That's in reduce, and that's in map phase. And before that, of course, we need the postings, which means that we need to do the indexing first, or at least assume that the index is there. Okay, so for that we did this decomposition, and this is very important in such problems. You need to think what can be done in parallel, completely independent, and how you can aggregate results. How can you aggregate intermediate results? Here in the problem, the intermediate results were the partial contributions. So that was the key idea. Once you get this idea of computing partial contributions, which is completely different from the trivial idea which we usually think of, which is let's get every pair of vectors and compute the similarity between them. Okay, we decomposed it completely to loop over terms, to go through terms. And this loop, if you think about it, if you now look at this algorithm, each iteration in this loop is completely independent of the other. And that was the key idea here. Because if we manage it to think about it that way, that means that each of these terms can be handled in a different mapper, or a different map function. Okay? And the process will be very easy to do. Yes?
Just now, think about something
Yes.
we discussed before in the first part about having the term and document as a key.
The term and document as a key. We didn't say that here.
No. So why we did this solution? How we will use only we need only the term as a key for the posting.
Okay. Let me clarify one thing. Seems like it's confusing to you. The output of the indexing, what will be the type, what would be the format of the output in the indexing phase? That we discussed in the first part.
One,
The final output, yes.
term,
Yes, the output will be term as a key and posting lists as a value, right? So we'll have one term here and the posting list here.
yeah, but I'm just confused why we were discussing having the term and document
That was to produce this
in the process.
in the process, but eventually the index will be term and posting list, and that will be the input to the second job. Is it clear now? What we did in the details was to make the indexing efficient, but eventually we'll have this. We will not have, of course, term and document number here. That's not an index. The index is the term as a key and the posting list as a value. Okay? But we did that trick because to control the intermediate output. Okay? Okay, so now the composition will be like that. The term contributions will be in the map, and this summation, of course, will be in the reduce. And we need, of course, the indexing as a step, as a first step. So that's the indexing that we saw before. The tokenization will happen here, emitting the individual outputs for each term, shuffling. Then we get the posting list. So this step is exactly what we did before. Nothing new here. With all the tricks if you want. Okay, with all the tricks that we discussed in the first part of the lecture. Eventually we'll get this posting list. Of course here it doesn't show the term and the key and value, but the key will be the term and the value will be the posting list. This step is this part. And this whole indexing for this problem is to get us to this part, which will tell us exactly which terms appear in the intersection of every pair, but separate. Yani we don't have the intersection of one pair together. They are completely distributed. That's the beauty of MapReduce, is to do this nicely. Okay, all the information is there, but it is distributed. Okay, so by that indexing, we got to that concept that we only need the terms that appear in the intersection of pairs. Where is that encoded? It's encoded in the posting lists. Okay, is that clear? Questions here? Now let me show you a specific example. As I told you, this version happened in version of slides was a bit old, so you'll see Clinton and Obama and Romney, not Trump anymore. So in the map, here I just encode the document IDs by figures and by shapes and colors. So that's nothing new here. We'll emit the key and values, the key and the term and document number, and we will shuffling will group, and reduce will produce the final posting list. So nothing new here in indexing. Now think of this as the input, so this whole output as the input to the second MapReduce job. Okay, so the pairwise similarity now will be done this way. The map will multiply weights, and the reduce will sum these partial contributions. Let's see what will happen in the example. Now, this is the posting lists. Clinton appeared in these documents with these frequencies. Let's assume that these frequencies are the weights, just for simplicity. So what will happen in the map phase? Each posting will be input to the map function, right? Now, can you tell me what will be the output of the map function that will handle the first posting, the term Clinton? Clinton? That will be the output. So now the map function, I don't want to show it. So the map function will take this posting list. Okay, what will be the output from the map function? Amen?
We need the document IDs, so for example,
triangle and
the square, for example.
The square, okay.
And the weight, which is
So that will be the key. And the value?
The value will be 2.
Will be 2 times 1, which is 2. Okay? And
then triangle and circle.
And then triangle and circle. Again 2, because 2 times 1. Then?
And then the circle and square.
Circle and square. 1. Okay, is that clear? Okay. Now the order of the pair will that make a difference?
No, because you will sort it anyway.
Who will sort it?
No, it will be sorted by the
sorting
way. By the
function,
way.
we need to specify.
Yani, if we produce here triangle then square square, we'll have to make it also triangle and square for other terms. So this, because if unless we define the sorting for these two pairs to be the same, okay. But if it will be just exact match, then we should not produce somewhere. Of course, it will not happen here. Actually, it will happen, right? Will we emit anything from here? By the way, why not? There is no pairs. But here there is one pair, so we'll emit from here triangle and square. If we flipped the order here, it will not match with triangle and square from here, unless we explicitly in the sorting we say that these two things are the same. Okay. Just you can here. What are these? Forget about the shapes. What are actually these? Document numbers. I can just put the smallest first, for example. That's it.
It doesn't matter because the operation is not product.
No, it matters because of the next step, which is shuffling. Shuffling will group by the same key. So you want all of these values to be together. Okay, you have a question?
Can we specify in the partition function to send both of these to the same reducer? Is it possible?
Of course, it is possible, but do you need that?
If it goes to the same
If you just order them, you don't need to do any special partitioning. They will group together by default. Okay. The fact that we learned about these things should not tempt you to complicate things. Okay, you don't need to complicate it here. It can be easily implemented. Just order the numbers here. Okay. So we have these three pairs, and in shuffling, they will be grouped together. Okay. What do we need to do in reduce? We just sum to get the similarity for the pair. Where is the similarity matrix here? Distributed, right? It's not in one machine. It's distributed. These numbers are distributed over different files now, different output files. Okay. Just changing the way that we usually think about doing that in one machine. Now you have multiple machines. You need to think. One key idea here is to think what can be done in parallel. And don't think about trivial things. You need to really reanalyze the problem that you have so that you can decompose things that can be done in parallel. If you kept thinking about the normal way, the usual way of computing the similarity pairs, you will only think about, okay, I need pairs of vectors so that I can compute the similarity of this pair, right? It will not scale. You need to think differently here. Okay. Here's the example that is in the paper. By the way, I updated the readings. You should. This is a paper. This is the example from the paper. Of course, this is a toy example. So that's the indexing, and this is the pairwise similarity. It's exactly what we did. Okay. Any questions about this? Is it an easy idea? It's complicated.
Easy to understand, but come up with.
Maybe in your projects you can do something like that for your problem. By the way, you should start, and I know that we didn't get much still in the topics that we want to cover, but you should start thinking about what you can do. Now, at least you know you get somehow familiar with MapReduce. You know how it works, I hope. So you can think of what you can do in your project. Think of a type of data that you want to work with. It doesn't have to be text, by the way. I mean, up to this lecture, yes, we work with text. Next time we'll work with structured data. The 2 weeks after, or 1 week after, we'll talk about graphs. Okay, so think of what you are interested in terms of type of data and what you want to do, and let's start the discussion as early as possible.
You can use it in image processing.
Of course you can. Of course you can. Not expert in image processing, but you can, of course. Any question about this algorithm? Okay, this is a paper that was, I think, in 2008. Okay, in 2008, Hadoop was 0.16. What is the version now? It's 3.0.0. That was not even 0.2. Okay, at the time, huh? It's 3.2 point something.
3 something is now, but we are working.
Yeah, we are working with 3.0. Yeah, that was 0.16. Very, very initial version of Hadoop. I had at the time cluster of 19 machines. That was the cluster that was given by IBM and Google. Used a collection of about 1 million documents. I used specific similarity function, but it doesn't matter. And we did experiments with subsets of collection. I will show you now the results. So what is that figure? On the x-axis, so I told you that the collection that we worked with was about 1 million documents. Okay. Now we want to see how scalable the solution is. So you will see in the next slide the processing time of different sizes of data, different subsets. Okay, to see if we increase the size of the data, what will happen, how much time it will take. So on x-axis, this is the collection size. In NLP, by the way, we call it corpus. It's the collection. That's the collection size percentage. Okay, so that's 100% when we have the 900K documents. And on the y-axis, it's not the time, by the way. If you look at it, it's not time. What is it? It's the number of intermediate pairs. If you look at this slide, where is the phase where almost all the time is taken? Where in this 3 phases? In the map. You think it's in the map? In shuffling. It's not in the map. Okay? Think of the number of postings in the index. Okay? Each term has number of postings, right? We will process this in the map. Now how many pairs we will get for each term? Yeah, let's say that I have 10 postings. How many pairs I will produce from these 10 postings? How many intermediate records I will produce?
10 postings.
When we have n numbers, how many pairs we can get from these n numbers? Oh. Oh. Okay.
There is a way to calculate the combination.
I know that there is a way to I know there is a way. Okay, and that's what I'm asking for. What is that number? If I have n values, I want to choose 2 of them. Right? You remember now, right? This what is this? What is that order? Order of what? Don't give me the exact number. The order of what? Is it order of n? To get pair, and we did it already, right?
N power 2.
It's not n power 2. Oh yes, n square. Yeah.
N square.
Okay, I thought n times 2. You said n power 2 earlier, right? Yeah, I thought it's n power 2. Yes, it's order n square. Okay, exactly. It is n times n minus 1 over 2. Okay, which is order n squared. Anyway, why did we want this? I forgot. Yes, I was talking about the number of pairs, intermediate pairs. Okay, so every posting list, it's square the number of the postings in that list. Okay, with every term. So that's huge number of intermediate records. Okay, so that's why here we don't report the time. We just report, because it's indicative, and it's related. We just report the number of intermediate pairs in billions, because that's n squared. Okay? In billions. It's a huge number. So for the full collection, when we have 100% of the collection, we have 8 trillion intermediate pairs. Actually, this is in thousands of billions. Okay, so we had 8 trillion intermediate pairs. Just to give you an indication of the time, that was of course hours, maybe, I don't think days, but it was hours. Because the collection is small here, by the way. It's just less than 1 million documents. We're not talking about the size of the web. The size of the web is billions of documents. And you see here, this seems like also quadratic in terms of the size. It's not linear. This is not linear, right? Yani the time, it is quadratic, kind of quadratic. Or maybe exponential, by the way. Yani we don't know if the size increased after that, what will happen. But it's not linear for sure. Okay, type. Now, that's with this algorithm, by the way. And this algorithm, of course, we didn't do it with the trivial one because it won't work with MapReduce. But that's with the algorithm that we discussed. Type. This is huge, right? We have to find a way that is more efficient than that. So the story didn't end here. Okay. Now let's just give you some information about how terms actually appear in text documents. It's the power law distribution. So this is called, this kind of curves called power law distribution. What does that mean? It means that the x-axis here is you can think of terms, and the y-axis is how many documents, the document frequency of that term. You will see that very few terms appear a lot, and very few terms. Did I say documents? Very few terms appear a lot, and many terms, and most of the terms, didn't appear in much less number of documents. Okay, so they didn't appear a lot. That's what we call a power law distribution. Few terms. Sorry, I don't know why I'm saying that. Few terms, okay, have very high document frequency, and most of the terms don't have high frequency. Okay? This is typical, by the way. This is typical in text documents. So, very few terms dominate the computations. Remember, why are we interested in something like that? What is this document frequency? This document frequency is the length of the posting for each term, right? A document frequency means the number of documents in which this term appeared, which is the number of postings in the posting list of that term. Okay? So that means that if we think about the intermediate output comes from the pairs of documents in the postings, right? So the terms that appear a lot will contribute a lot of intermediate output in that problem, right? In that solution. Is this clear? So most of this 8, if we go back here, most of this 8 trillion intermediate pairs are actually generated by few percentage of terms. Okay? So we did that statistics. We found that the most frequent term in that collection was the term said. Okay? And it appeared, it contributed to 3% of the pairs. Okay? Just one term. One out of maybe millions of terms contributed 3% by itself to the pairs because it appeared a lot. The most frequent 10 terms contributed 15% of the intermediate records. Okay, so very few. We continued and we looked at the most frequent 100 terms. Most frequent 100 terms contributed with 57%. This is very interesting here. The most frequent 1,000 terms contributed 95% of the entire set of intermediate records. Why is that beneficial here? Why do we care about these numbers? First of all, by the way, for that collection, 1,000 terms is it's not even 1% of the terms, it's 0.1% of the number of terms. Okay? Right. Why do we care about these numbers? What do these numbers mean to us?
The accuracy
Of what? Now, these are giving us some indication of which terms are actually problematic in our computations, right? Because these terms that appear a lot, the most frequent terms, will contribute the quadratic number of their postings as intermediate records, as intermediate pairs. Is that clear? This by itself, remember this 8 trillion number, 8 trillion pairs? 95% of this 8 trillion pairs are just generated by 1,000 terms, which are just 0.1% of the total terms. Which means that if we ignored these terms, if we filter them out, how much time we will save, roughly? 95% of the time. 95% of the time. It's not just even 10%. It's 95% of the time. If we just ignored these terms. And if you think about it, these terms are most frequent. They are already everywhere. So they are not distinguishing. They are not really the terms that we should care about. So that was one key idea. And we call this, if we filtered out these terms, we call that DF cut, because we will filter based on the document frequency. So we'll cut out on some percentage of the terms. If we cut out 0.1%, then this is 99.9% DF cut. We will keep 99.9% of the terms. We'll just remove 0.1% of the terms, and we get a reduction in time, roughly, by 95%. So let's see if we do that, what will happen. Now we have multiple curves, right? Where is the original curve? This is the original curve, the one, this one. With the 8 trillion intermediate pairs when we have 100%. Okay? What are these other terms? So this is the no DF cut term, curve. That's the original one. If we used all the terms in the collection. Now, if we did the cut at 1%, I mean at 99%, which means that we will get rid of 1%, the most frequent 1% terms in the collection, we will get this blue one. That's huge, right? Huge difference. And in between, if we get rid of 0.1%, if we get rid of 0.01%, and so on. Of course, as we remove less number of terms, we get closer to the original curve. As we go more aggressive in removing terms, we go down. Okay? In that case, this point, which is at 0.1%, this is the 95% reduction. We get 0.5 trillion pairs instead of 8 trillion pairs. So this is 1/16 of the original size. Okay? Is that clear? Right. Where is the problem here? What are we doing here? Will we get the same numbers that we would get if we keep this 8 trillion pairs? No. Why not?
Because if we calculate the similarity for all the 8 trillion pairs, you will add a lot of intermediate, we call it intermediate weights.
Yes.
Similarity weights.
Yes.
So of course we will get a different one, but it will be.
So what is the relation between the values that we will get now and the original values? Will be bigger, smaller?
Will be smaller.
Smaller, right? Because we ignored many pairs, many partial contributions, right? It will be smaller. So you can think of this as an approximation. Maybe drastic approximation, we don't know yet. Okay, so with that slide, with that chart, we cannot tell whether this is drastic or not. It's drastic in terms of time, right? And it gave us huge advantage in terms of efficiency, right? Because now that will run much, much, much faster than before. In fact, I remember when I ran this, I was not able even to get this aslan. Yani I didn't finish this job. This job didn't finish at the time. Okay, and I had to do this approximation. That's how we came up with this idea. Okay.
If the goal is to establish the reasonable similarity between the
Exactly. Exactly.
and you don't care about those very, very common words that are appearing in all of the documents.
Exactly.
You care about words that are less frequent.
Exactly. So it was
It makes
kind.
sense- It makes sense. I would say that what you did is making the result more accurate towards the real goal than it was before.
Well, we'll see. We'll see. But yes, it was kind of win-win situation. We remove things that we think that they are not of value, and that makes the that made the computations much more efficient. Okay, but still we wanted to know the actual effect. Okay, so again the story didn't end here. We have to show the effect of doing these approximations on the accuracy of the results. We did that with an application. Okay, we are not here to say the details about the application, but it was more like this application that we mentioned earlier. And this is now the quality of the results. Okay, this is on the x-axis is the DF cut percentage that we experimented with. We experimented with several DF cuts. Okay, where is the one that we were talking about? The one that we saw here, 99.9. So that's this one. Okay, here. What is on the y-axis? This is the performance measure. Forget about the meaning of that, but of course, as it goes up, it's better. Okay, so that's the performance. Now, 100% DF cut. What does that mean? Full. No approximations at all, and this is a relative performance, by the way. Yani the performance for this will be 1. That's relative. We just divide by that performance to see how much we lost if we do the approximations. So that's 1 when it is full. Now look at what happens when we do 99.9%. That's what we get. Okay. This is what we lose. Okay, so we lost 2% in effectiveness. Actually, we hope that it would be better, but it wasn't. It seems like we were more aggressive than we should. Maybe in that 1,000 terms, there were some terms that are actually of importance. But with dropping only 0.1%, we got 95% more efficient on the expense that we lost just 2% in effectiveness. Okay. Yes.
You said these words were only 1,000 words, right?
At 99.9%, I think yes, it was 1,000.
So we can easily go through them and find out if there is a word that should have been included. I mean, if there is an important word.
How can we do that automatically? It's not straightforward. It's not straightforward.
You could do the referencing, and they are let's say data sets with the most common search terms, for example, that are most relevant. So you could do referencing like that.
Yeah, but it's not straightforward, and it's not. And remember, now if you put back some of these, you will not get 95% speed up. You get less. So it's a trade-off. You need to play with, and that's the trade-off. That what you see here on that slide is the trade-off. Okay, as you move left to the left, you get higher, of course, speed up because you are more aggressive in moving the terms. But you see here, for example, will that be satisfactory to get 75% of the effectiveness? I don't think. Okay, it depends on the application whether you are willing to lose some of the quality of the results for the speed up. It depends on the application. For that application, 2% was okay. 10%, I wouldn't think that it would be okay. So it depends on the application. Here, 2% and with 95% speed up was great.